Okay, so in this video, we're going to talk about finding the nth root of a number. You may be familiar with, say, square roots and cube roots for real numbers, but we're going to be able to find the nth root of any number that is a complex number. So let's just look at just a basic square root situation to begin with. So let's say we have 4, and we have this equal to x squared. If we want to solve for x, we actually know this has two solutions. We could take the square root of both sides, and then we'll have x is equal to plus and minus 2. So that's great for 4, but what if you were trying to solve, say, something like x squared equals 4i? All of a sudden, this is a lot more complicated. Like, how are we going to do this? And so what we're going to do is we're going to leverage the Maus Theorem. Our last video talked about the Maus Theorem, which said that if you have a complex number z written in trigonometric form, so z is equal to r times cosine theta plus I times sine theta, you can do this. You can raise z to some power n, and that's the same as saying r to the n times cosine n theta plus I sine n theta. And before we had n just being regular numbers like 1, 2, 3, 4, etc. But it turns out that you can actually use different n's. In fact, you can use fractional n's. So instead of using n, we can use 1 over n. So the Maus theorem has as a direct result z to the 1 over n is equal to r to the 1 over n times the cosine of 1 over n theta plus I times the sine of 1 over n theta. And this will give us a solution to the root problem, because if you remember, if you write something with a square root, you can really write it as to the 1/2 power. But you'll notice that square roots have two solutions. Cube roots actually have 3 solutions, and so on and so forth. Nth roots actually have n solutions. This only generates 1 solution. So what do you do to generate the other n minus 1 solutions? Well, what you'll do is you'll just add to the angle that you find 360 over n as many times as you need to until you have the right number of solutions. This seems pretty weird, but let's just do a couple of examples here, and we'll see how it works out. So let's write, I want you to copy this down before we go to the next thing. All right, so what we're going to do is we're going to solve that equation that we had that looks so intimidating. X squared is equal to 4i. So what we want to do is we want to write our number here in trigonometric form first. So if we write 4i out, if we draw 4i out, it shows up right here, because this is really 0 plus 4i. So it shows up here on the positive real axis. You can find its r the way we always do. R is equal to the square root of 0 squared plus 4 squared, which is a squared plus b squared, which is just 4. Now to look at the angle, that is not too hard to find. It's just on the positive imaginary axis. So the angle is actually just 90 degrees. Okay, so we have this situation here where x squared, could be z squared, but I'm going to use x squared, is equal to 4 times the cosine of 90 degrees plus I times the sine of 90 degrees. Okay, now we're trying to solve for x. So what we're going to do is we're going to raise both sides to the 1/2 power. The 1/2 power will reduce this, so we'll get x is equal to 4 to the 1/2 times cosine of 1/2 times 90 plus I times sine of 1/2 times 90. Okay, so this is just a direct result of Maus Theorem. We had this raised to a power, 1/2, so we put the half here, here, and here. So let's reduce this guy. 4 to the 1/2 is the same as square root 4, which is 2. Cosine of 1/2 times 90 is really cosine of 45 degrees. And then we have I times sine of 1/2 times 90, which is again 45 degrees. But you notice here that this was a square root. So we need 2 solutions for this, not just the one solution we have. So what we're going to do is we're going to add 360 over 2 to our angle. So the other one we're going to have is, so 360 over 2 is 180. 2 times cosine of 45 plus 180, which is 225 plus I sine 225. So we have our 2 solutions here. And we generated this second solution by taking our initial basic solution and adding 360 over 2, which was the power that we had here. And this is because these roots are equally spaced around a circle, which makes it easier to remember. And what we can do is we can convert these down into standard form. So if we have 2 times cosine 45 plus I sine 45, this is equal to 2 times square root 2 over 2 plus square root 2 over 2i. And this reduces to just square root 2 plus square root 2i. This is one of our solutions. The other solution is 2 times the cosine of 225 plus I sine 225. So this is equal to 2 times negative square root 2 over 2 minus square root 2 over 2i. And we're going to reduce in the same way, and we're going to get negative square root 2 minus square root 2i. So this and this are the solutions to this equation. Or we could think of it as these are the square roots of 4i. So let's do one with more than 2 solutions here. Let's look at x cubed equals 8, and we're trying to solve for x. So first things first is we're going to write this down as 8 plus 0i to get it into that more familiar complex number form. So I like to plot my stuff. 8 plus 0i is actually right over here on the real axis. So we can find our r. Our r is square root of 8 squared plus 0 squared, which is square root of 64, which is just 8, which is nice. And then we need to find our theta, but if you look, it's just here on the positive real axis, which is the same as the x-axis, basically. So we know theta is actually 0 degrees. 0 degrees. And what we'll do is we'll rewrite this equation like this. X cubed is equal to 8 times the cosine of 0 plus I sine of 0. And we're going to find the solution to this by raising this to the 1/3 power. But if we do that to this side, we got to do that to this side as well. And we can invoke the Maus Theorem. So x, after these reduce, is just 8 to the 1/3 times cosine 1/3 times 0 plus I times the sine of 1/3 times 0. And we can reduce this. 8 to the 1/3 is the cube root of 8, which is 2. And then we have cosine of 0 plus I times sine of 0. Now you notice we have one solution here, but this was a cube root. So we actually need two more solutions. So we're going to add 360 over 3, or 120, to get our other two solutions. So the other two solutions we'll have are going to be 2 times the cosine of 120 plus I sine 120, and 2 times the cosine of 240 plus I times the sine of 240. So here are our three solutions. We got this basic one from using the Maus Theorem, and these last two by using the fact that they're equally spaced around the circle. So we just divide 360 by whatever our power is here to get a spacing, and add that on until we have the right number of solutions. And we can convert each of these into standard form. So if we have 2 times cosine of 0 plus I times the sine of 0, this is 2 times 1 plus 0i. 0i is 0, so this is just 2. Excellent. 2 times the cosine of 120 plus I times the sine of 120 is 2 times negative a half plus square root 3 over 2i. So these 2's will all cancel out here, leaving you negative 1 plus square root 3i. And then the last one is going to be 2 times the cosine of 120 plus I times, sorry, not 120 because we added 120 again, 240 plus I times the sine of 240. And this is equal to 2 times negative 1/2 minus square root 3 over 2i. And when we distribute that 2 through here, we get negative 1 minus square root 3i. So our three solutions to x cubed is equal to 8 are x is equal to 2, negative 1 plus square root 3i, and negative 1 minus square root 3i. So what do we do in general? You write out your number in trigonometric form, invoke the Maus theorem with the fractional power, 1 over whatever the power is here. That'll give you a base solution. And then you just leverage the fact that these are equally spaced. And so you do 360 divided by whatever this power is, and then add that on to the angle that you had initially here until you get down to the right number of solutions. And there should always be n solutions for x to the n. Hopefully that's explains things enough here. If we need to do some more examples, I can do that in another video.